This is our senior project presentation. We did our senior project for Gulfstream Aerospace, and our topic is paint hanger improvement. My name is Bryn Hellickson. My team members consist of Pauline Tasci, Oscar Sanchez, and Emmanuel Delgado, and our advisor was Dr. Mirzaei.
So first off, a little bit of an overview. The first thing we're going to go through is some company background, move on to project objective, plan of attack, alternatives that we went through, and lastly, solutions and suggestions for Gulfstream Aerospace. So for company background, Gulfstream was founded in 1958. Roy Grumman introduced actually the first Gulfstream plane, and this was a big deal. This was a big deal because this aircraft really revolutionized aviation because it was the first business-built aircraft rather than commercial. This made it an industry high flyer. Project objective for this senior project is in fact to decrease the paint cycle time by 3 days at Gulfstream's Long Beach hangar. Long Beach is tasked with all exterior of the planes. Planes are sent from their headquarters in Savannah, Georgia to Long Beach, and paint and prep happen in Long Beach, California. So for a plan of attack, the first thing we really went through is gathering data and analyzing the current system that they do have, identifying room for improvement, providing alternative solutions to Gulfstream, evaluating those alternatives that were chosen, and lastly, final suggestions for Gulfstream. Our first step, like with any project, was to do data collection and analysis of that data. This phase included a lot of things, but some things we'd like to talk about are some time studies, value stream mapping, utilizing lean, regression analysis in order to forecast completion time for every aircraft in the year 2020, facility layouts, worker hour studies, and lastly, rework studies. So there are two processes within this prep and paint process. It's prep and paint. So for the prep process, it takes approximately 6 days on average. This is a process map of it. It's kind of broken down and minimized a little bit just so it's easier to understand. Some things that are important are a lot of masking, priming, and sanding, inspection and demasking, and that really ends the prep process. Next up is the paint process, which on average takes 8 days. This is also a cleaned up version of the process map. And as you can see, this involves a lot of masking, laying out, painting, more demasking, inspection, and really ending the paint process. So again, prep takes 6 days, paint takes 8 days, taking 14 days total. This is the current facility layout for the prep hangar. There are 3 hangars, prep, paint, and layout. We decided to focus on the prep hangar, as we'll get into, so when we go through other data analysis later on. Anyways, this is really, everyone is coming towards the plane. This plane is parked, and workers, as well as resources and carts, shelves, anything like that, everyone is going towards the plane. It's not an assembly line per se. It's really bring everything to a centralized location and work from there.
Value stream map. The purpose of the value stream map is to identify and remove or reduce waste in value streams, thereby increasing the efficiency of a given value stream. The main 4 processes are preparation, layout, paint, and inspection rework. There are 2 shifts with 12 operators. Takt time is 7.5 days. Process lead time is 18.45 days. The value added time is 267 hours with a ratio of 90%, which means that takes 90% of the time to the work is being completed. Forecasting linear regression. The dependent value is the actual days that it takes to complete the entire process. The independent value is the number of aircrafts. Analyzing the data from 2017 through 2019, we were able to forecast the movement of the future completion time that might take for 25 airplanes in 2020. Here is the equation of the regression analysis that shows the negative movement that in this case is a good thing, which means the completion time is being reduced by time. The R squared is 68.28%, which shows that 68% of the time is close to the linear equation. The p-value is less than 0.001, which means that the process is statistically significant, which in any case of presenting a null hypothesis, it will be rejected with respect to this value. Therefore, we reject the null hypothesis and accept the alternative hypothesis. This is a visual representation of the days over schedule time for 2017 through 2019. Looking into the whole process and knowing that the process time should meet the attack time of 7.5 days, preparation is the longest process at 6.11 days, which shows that it is the bottleneck. This is the current primary standard operations procedure. The flow chart shows how the operators move in the process. The current process simulation, the planning statistics for 2018, 60% of are completion aircraft and 40% are service aircraft. It shows with a visual representation of the flow of the simulations. The overall process time, based on the simulation, it takes 15.7 days and requires a 14% overtime on every aircraft. The rework analysis, total time of rework in 2018 was 11,716 hours with an average of 450. We use an IMR chart, which is a representation of an individual moving range. It helps identify when the process goes out of control.
From the quality control chart, we were able to move on and try to account for the amount of rework in certain parts of the airplane, and we noticed that the most defects were from the left front, and that accounted for 20% of the rework. From then we were trying to figure out why it led to the left front being the most. What was the problem with the left front that had to be reworked? We created a fishbone diagram to map out the process, and we determined that the material was not sufficient. It was a little too thick and it didn't quite fill the areas, the smaller areas within the rivets of the aircraft. So we came down to the conclusion that that the chromium-based primer leaves voids in the rivets, and it's only noticed until once the aircraft is finished with the final step that they're able to notice, once it dries, where the certain areas that the paint did not fill. So we then presented alternatives to try to fix the solution, which was alternative 1, which is reduce work by changing the primer. Alternative 2 would be to hire more people to work in the prep area. This initial alternative 2 was then actually split into several alternatives that will be later discussed. For alternative 1, which was to change the primer process, we had to pretty much create a new time study, and we had to make a simulation based on those time studies. Some of the advantages of the non-chromium process was that the original prep process used chromium, which was very toxic, and it took a very long time to spray, and it dried very quickly, so it didn't reach certain areas. The new prep process uses a water-based primer that would be better coverage and less toxic to the environment. The results for the alternative 1 came out to have actually the new output down to 14.7 days, which is a 7% reduction overall cycle time, which is okay, but it still requires over 10% more overtime work at prep, which is not the optimal solution. The throughput did increase to 3 aircrafts per year. This is just an overall view of the non-chrome process, which begins with the preparation, the detergent wash, masking, applying the coat, sanding, applying treatment, corrosion, inhibiting primer. That's where pretty much most of the primer for the new process was being implemented to. Then it actually moves on to an inspection to make sure that we're moving on. Before we actually sent it to paint, they had to be inspected to make sure that there's minimal minimal amount of rework that had to be done in the overall process. Then we move on to washing and spotting with iodine, demasking, and ending the preparation process. From the implementation of the non-chrome prep process, the results showed that the cycle time actually decreased to 5.9 days from the original 6.4 days, and which is a total of 7% reduction. And we wanted to further reduce the cycle time, and we discussed with worker and management of two to three more alternatives that came about.
Now with the new data that we have collected, we decided to put that into a new value stream map with the cycle time of 5.9 days on prep. This helped to bring our value-added ratio up to 91%. We then went on and decided that we would like to try to improve the cycle time even more. So we presented a few alternatives to Gulfstream, and these were the ones that we both collaborated on and decided were the best to pursue. So alternative 3 is to change the worker shift scheduling to a 4/10s from a standard 5/8s, 4/10s being that they will now work 4 10-hour shifts per week. Alternative 4 is to increase the prep worker headcount at the prep station from 6 on first shift and 6 on second shift to 8 on first shift and 9 on second shift. And then alternative 5 was to combine both of these alternatives to hopefully bring the strong suits of both together. So for alternative 3, we created a simulation, and we actually found that with this scheduling system, it increased our cycle time by 1%, and that's just due to where the breaks fell in the processes and stuff. So this actually brought the new cycle time up to 14.74 days and still requires 10% overtime work on prep. For alternative 4, we simulated it, and we found that we actually got a 13% reduction in the overall cycle time for an aircraft, which brought the overall time to produce one aircraft to 13 days with 0% overtime at the prep station. And this allowed prep to no longer be the bottleneck and actually shifts it over to the paint station. For our final simulation, alternative 5, we actually found that it decreased the cycle time by 14% and brought it to 12.95 days with 0% overtime at prep. This is actually 0.05 days less than just the 8 and 9 scheduling, and decreases cycle time by an additional 1%. Here's a summary of the alternatives that we presented and did simulations on. We are deciding between the both that the 8 and 9 scheduling system is probably the best, as it requires us to hire new workers without having to change all of the current prep workers' schedulings and live and disrupt them in some kind of manner. So alternative 1, we did a return on investment analysis, and this is just a graph showing that for the next 3 years, each year they will be saving $103,000 just on labor costs by switching to the non-chrome process, as there's no longer any overtime work, which was costing them a lot of money. And it actually increases aircraft throughput by 2 annually. We then did a return on investment analysis for alternatives 1 and 4 together, meaning that the non-chrome process, which is already implemented, combining that with 5 more workers. And this actually increases aircraft throughput by 5 total annually, and can possibly net them an additional $100 million a year because of how much they are making on each aircraft. So here's our conclusion. We decided that the best course of action for them is to both implement alternative 1, which they have done, as well as implement alternative 4, which is to hire 5 new workers. This will help us to reach our goal of reducing the overall cycle time by a total of 3 days, which was our original goal. This also equates to a 21% reduction in overall cycle time per aircraft. From the data we've collected from them on the new process, even though there's only a few aircraft so far, we've found that their rework has decreased by 14%. And with both alternatives 1 and 4, their return on investment will be over 6,000% at year 3. So for the future forecast, we forecasted that they will have 25 completion aircrafts to consider for 2020 calendar year. And completion aircraft by the end of that year should take them only around 12 days as they get the new processes dialed in and all the workers get hired. And then some future considerations that we are going to leave off with them is to implement some new lean and continuous improvement ideas. One of them being 5S for their prep carts, as right now they're very disorganized, and we observed many workers going over to get their sanding tools and all their hand tools, having to search and look around and just not finding them right away, which is just obviously taking up a lot of time. And then provide a Kanban on the supplies. Right now for their prep supplies as well as their paint layout supplies, they get stencil kits, and sometimes the stencils get ripped or lost and they have to go take them from another kit, and they just wind up not knowing how much supplies they have or when to order, and they waste a lot of time waiting or searching for those supplies. So these are just some recommendations we're going to leave with them. So that is the end of our presentation. Thank you for listening, and any questions?